Hey everybody, I want to make a video here going over some of our basics of hypothesis testing and connect it to things with the randomization distribution, as we're calling it. And like the last video, I'll talk a bunch, but the real key is that this is more like a supplement. So hopefully you've read the chapter and thought about these ideas a little bit, and this will summarize some of them. I'll efficiently talk about things to put it in the bigger picture, and then show you a couple of examples to show you where to click and how to interpret things. But you should be able to do everything easily with the book chapter and with the instructions in the discussion activity. So there's nothing super special about anything I'm saying here, other than maybe just the words and how I put them together, perhaps. So anyway, so let's set the stage. What are we doing here? Well, remember the last unit, our whole objective was to find where the population mean or proportion of something might be. We're trying to estimate the value for an average body temperature or for mean difference in test scores, stuff like that. Well, now we can do something different. We can say, is the actual body temperature, population mean body temperature, 98.6 degrees? We can ask questions like, is there an actual difference between USA and Finland on the PISA test scores in the population on average? So the thing we focus on is making a claim. Hypothesis testing and the randomization distribution are about making claims and testing them and seeing how much statistical evidence there is for a claim we want to make. So we're not trying to estimate the value of anything. We're just trying to test a claim. That involves a quantitative number. So that's where we're going here, and that's why we do this. We make ideas about things in the world and what values might be based on experience, previous research, judgment, and then we go test to see whether or not our hypotheses are true or not, and we can use statistical evidence to do that. So again, in summary, with what we have listed here, our goal of hypothesis testing, we're making a claim about the population. And I want to stress the word population as we did in bootstrapping. Hypothesis testing is about the population. And remember, the thing we measure in the population, the average body temperature, the average income for all Minnesotans, that is called a parameter in the population. And then we use our data, our sample, we use that to make an inference about the population. And again, with the terminology, what we call a parameter in the population, we call a statistic in the sample. So I just wanted to reiterate that. So if the situation we're looking at is average income for all Minnesotans, the population parameter is the average income for all Minnesotans. And the sample statistic would be the average income in the sample. And that's how we connect statistic to parameter and sample to population. So hypothesis testing, we formulate everything from a population perspective, and our conclusions are about the population because that's what we care about. That's what we want to say something about. But in order to do that, we only have a sample of data, so we actually work with samples and samples of data and statistics. Great. All right. So in general, for hypothesis testing, first we have to define the thing that we want to measure. So whether it's average body temperature, average income, that's the parameter of interest. That's the idea. And then from there, the thing we want to measure and the idea that we may have about it are what we're hypothesizing, perhaps. That helps us make our null and alternative hypotheses. So here's the logic when we do hypothesis testing. We have what's called a null hypothesis, and we have what's called an alternative hypothesis. The alternative hypothesis is that which we think is true. Let me say that again in a different way. The alternative hypothesis is that which we have some suspicions about, that we have a guess about, that we have a hunch about. So for example, if we had gathered this USA and Finland PISA score test data, and we just looked at it a little bit, and it seemed like, say, Finland was scoring higher than the United States, just estimating by looking at the data. Our alternative hypothesis is that Finland is, on average, performing better than the United States. What we suspect is true is the alternative hypothesis. Therefore, what our null hypothesis tends to be is something of no effect, or something of no difference, or something. Basically, the null hypothesis is something that we want to prove wrong. And you'll see why as we go about this. But that's how we set this up. So again, the suspicion that we have in mind, that's our alternative hypothesis. And therefore, the counter situation to what our suspicion is, that becomes our null hypothesis, or the uninteresting, or the things as they are hypothesis. So let's work that through a little bit. So after we define what we're interested in measuring, and then make an idea, a judgment about it, and make our hypotheses, what we want to do is say, okay, let's say my null hypothesis is true. If my null hypothesis is true, then what might I expect my world to look like? And this is where the randomization distribution comes into play. The randomization distribution is very similar to the bootstrapping distribution. It's a distribution of simulated means, but it's simulated assuming that our null hypothesis is the true effect that's out in the world. We make that assumption, and we simulate with a randomization process what kinds of samples I might get if the null hypothesis were true. So just like the bootstrapping method and bootstrapping distribution was mimicking what kind of samples we might get from the population, the randomization distribution and randomization for hypothesis testing is doing the exact same thing, with the one twist that we are making adjustment to assume that the null hypothesis is true. And that has an implication for how we run this randomization distribution, how we interpret things. Again, we'll see that when we go through an example, but these are the words and the terminology and the language for the idea. After we run the randomization distribution in our simulation, then we can find something called the p-value, which we will talk about. I'm not going to try to define everything about the p-value right here, because that's kind of a lot to just do in words with no other assistance. After we make our randomization distribution, we find the p-value, which, as it's defined here, probability of obtaining the results as or more extreme that we actually saw in our sample, assuming the null is true. And then based on this magical p-value thing, which we will unpack and demystify, then we can decide whether or not we want to reject our null hypothesis. And if we reject our null hypothesis, that by default means we find support for our alternative hypothesis. And remember, the alternative hypothesis is that which we are suspecting might be the case. Our alternative hypothesis is what we think is going on in reality. So to refresh, we use a p-value. The p-value helps us determine whether or not to reject the null hypothesis, and then that gives us evidence for what we thought might be going on, or it does not give us evidence for what we thought might be going on. And then we make a conclusion from there. So that's the language behind the steps we're doing here. And again, this may be a lot of weird abstract stuff. I'll just be straight up. Hypothesis testing is actually very philosophical, and it's very classic logic oriented. So it's not so much mathematical in any way. It's not even almost, it's more than just statistics. It's actually very philosophical, sort of scientific philosophy, scientific logic going on. And that can throw people. But again, we'll unpack this. So let me just back up here. When we find a p-value, and if we find a small p-value, that lets us reject the null hypothesis. This is called statistical significance. When we reject the null hypothesis, we have found a statistically significant result. And what that means is that the sample we got, that data that we have, was unlikely to occur from sampling variability if the null hypothesis were true. Statistical significance is saying that the data we have and the sample mean that we got from that data was unlikely to occur, to happen, to come to us if the null hypothesis were true. So statistical significance is ruling out simply random chance and sampling variability. When we rule out sampling variability for why we obtained the data that we have, assuming some null hypothesis is true, when we reject that null hypothesis, statistical significance means something other than randomness is going on that gave us the result that we did in our sample. And if something else is going on, for example, if the mean difference between the Finland and USA scores is statistically significant, then we're saying, oh, that wasn't just a random fluctuation that led to those difference in mean PISA scores. There must be something going on there. Maybe it's ability. Maybe it's testing conditions between the two. Hard to tell. Point being, statistical significance means there's something else going on there that's not just fluctuations. And that's the idea we're working with here with statistical significance. Now, in the counter case, we may find a p-value that's not statistically significant. We may find a p-value that indicates a high probability of obtaining what we got from our sample, assuming the null is true. And if our null is true and it were to give us a sample of data that we have that has a high probability of occurring, then that's no reason to reject the null hypothesis. The null hypothesis, if we assume it's true and it produces a distribution that gives us something that would be likely to occur, we have no reason to discount the null hypothesis. And so when we say results are not statistically significant, we fail to reject the null hypothesis. We don't say the null hypothesis is true, and I'll address that in another way through email or in person. We just say we fail to reject the null hypothesis, and we don't find evidence for anything. But we will do that with a couple of examples now. So I'll pause this and move on to the next video.